Welcome back to the 2025 Everybody Codes. For Quest 10, today we are doing something on a chessboard. So, our chessboard has variable size and has a dragon and a bunch of sheep on the board. And if a dragon and a sheep end up on the same square, the dragon immediately eats the sheep. So we're told that the dragon moves exactly like a knight in normal chess. So it explains it here. I'll show you via a diagram. If we have a dragon in a square like so, then the dragon can move in an L shape, taking one step in one direction and two steps in another. So for example, it could go two steps this way and then one step this way. It could go two steps up and then one step left. It can go two steps right and one step up, and so on and so forth. And so overall, the dragon is able to make moves to any of up to 8 spots. Now, if it is against an edge or a corner, it will be able to make fewer moves, but otherwise, if it's out in the open, it can make up to 8 different moves. So that's how the dragon can move. We decided to practice the dragon's moves a bit, so we're given an example chessboard with one dragon on it and a bunch of sheep. We want to figure out how many sheep are within 4 moves of the dragon, meaning if we can move the dragon up to 4 times, how many of the sheep are we able to eat? So in this example, we're just checking up to 3 moves, and we can see that at 0, 1, 2, and 3 moves, these are the pieces that the dragon, these are the squares that the dragon is able to reach in that range. And then if we overlay that with the grid of sheep, the X's mark how many sheep we're able to eat. And so let's copy this sample case over to our input. We'll begin by grabbing a grid, which we can do by turning each string into a list. We don't need to turn the rows into lists, but I prefer to do that just to make things easier. Occasionally it does matter, especially if we're trying to edit the grid at any point. So we'll do that. And that'll give us our grid. And so the first step is we're going to find where the dragon is. So let's find the initial dragon position. So we're going to go through each row and then each value, where R and C represent the row and the column index respectively. So if val is equal to D, then set dragon equal to RC. And so at the end we should have the coordinates of our dragon's starting position, which is in row 6, column 6 using 0 indexing. So now we want to check what all of the possible squares for it to reach are. So we'll track that in a set called let's call it range, or no, that's a built-in. Let's just call it S. And initially, it will just contain the dragon's starting position. Now, to make things easier for ourselves, let's define a utility function called dragon can move to, which will take the dragon's current position and return the positions it's able to move to. So, there are 8 possibilities. We're going to... The possibilities are plus or minus 1 in the row direction and plus or minus 2 in the column direction, and then vice versa as well. So if we ignore the plus versus minus for now, that basically means we're either moving 2 rows and 1 column, or 2 columns and 1 row. So represent that with difference row and difference column in 1, 2 or 2, 1. And then we'll determine if we're adding or subtracting. So for sign on the row direction and sign on the column direction, we have the possibilities of adding in both directions, adding the row and subtracting the column, subtracting the row and adding the column, or subtracting in both directions. And then the position that we would be attempting to move to would be the row coordinate of the dragon plus the sine of the row moved times the distance moved, and likewise for the column. And then if that is at least 0 and less than the length of the grid, let's store that here. Let's get the number of rows and columns in the grid. So if the row index is between 0 and the number of rows, and the column index is between 0 and the number of columns, then we'll add it to the output. And so just as a sanity check, let's see where our starting piece is able to move to. We get these squares, which looks correct to me. So then we just do 3 iterations of this, where we will take our set and we'll add the following set. So as a reminder, the pipe operator for sets is the union. It returns a set containing everything in either set. And union equals is similar to plus equals. It basically is shorthand for S equals S union with the right side. So for each dragon position that is currently possible, we will use dragon can move to get the positions that that position is able to reach, and then we'll flatten it by doing this for spot in this. And so we're doing a double list comprehension here, which basically means for each dragon in S and for each spot that the dragon can move to, we'll put the spot in a set. And by having these both flat, as in we're not doing something like, as in we don't have any like square brackets within this, this means that all of these will be flattened out into one set. And so now if we print out S, we'll get a full set of all of the coordinates that can be reached from the starting spot within 3 moves. Technically, there's a bit of redundancy here because we're going to check the possible positions from the starting place 3 times, but it does not actually matter here. So let's just do this. And then finally, we need to determine how many of these represent sheep. So the total will be for each row and column position in S that we can reach, if the letter in the grid at that position is equal to S, then we want to add 1. And so again, because true and false in Python are the same as the values 1 and 0, we can just take the sum to count how many of the row and column positions in S match this condition. And so that'll get us our answer for part... Sorry. Changing that to 4, that'll get us our answer for part 1. Moving on to part 2, we can see that the sheep are able to move 1 square towards the bottom of the chessboard. And during the game, the moves alternate dragon, then sheep, then dragon, then sheep, etc. We're also told that there are hideouts on the board that are marked with pound signs, which protect the sheep from the dragon. In other words, if a dragon and a sheep are both in a hideout, then the sheep will not get eaten. They can both move onto the hideout square just fine. And the goal of the sheep is to escape before it gets eaten by the dragon. And if a sheep reaches the lowest row on the chessboard and then moves down, it will be removed from the board as a survivor. Basically, once they reach the bottom of the board and move down another row, they have successfully escaped the range of the dragon. So we imagine a large chessboard with a lot of sheep and a lot of hiding spots, and we try to simulate this game over 20 rounds to see how many sheep can be eaten in all possible moves for the dragon. All of the hideouts are empty at the beginning, which means that all of the pound signs represent a hideout with no sheep under them. And we can assume that the sheep are stupid, so they might move into a square where the dragon already stands. And if that happens, then the sheep gets eaten immediately. So for this instance, we want to track which sheep is getting eaten, so we can't just check the square where it gets eaten, because we also need to determine which sheep that was, because multiple sheep can occupy the same position over the course of the game. So we're going to keep a set indicating which sheep has been eaten, and the way I choose to do this is by simply tracking the starting coordinate of the sheep. So what we can do is we can move all of the sheep down each turn, but the way I chose to solve it was instead to just go off of the number of turns that it has been and look for where the sheep would move to. Because each turn we know that each sheep will move down by 1 square. That means that after 3 turns, we can tell whether or not a sheep will be in a square by looking up 3 rows. So this time we're going to need to keep track of which turn it is. And this time we're not going to be taking the union of the set because we want to determine what the possible positions for the dragon to be in at that turn are, not up to that turn. So we're going to just remove the pipe and just say s equals all of the possible spots for the dragon to be in. And then we'll check which of those represent an eaten sheep. So for each row and column that the dragon can currently be in, we want to check 2 possibilities. The first possibility is that the dragon has landed on a sheep and eaten it. In this situation, we'll want to check up turn number of rows. So we can imagine that when none of the sheep have moved, which would be in the first iteration when turn is equal to 0, that means that we want to check the actual position of the dragon itself. So that'll be r minus turn. And then the other spot we want to check is where the sheep have moved to from there. So during the first turn, the dragon will first move, and then all of the sheep will move down, which means that if any sheep are currently above the dragon by 1 position, then they'll move down and get eaten. So we also want to check r minus turn minus 1. Basically, we want to check the row above it. So we'll do another layer of looping for sheep row in the 2 possibilities of either being in the dragon's position or above it. And then we will establish a condition. So this will all go in a set iteration where we're keeping track of the starting position of the sheep, which is at SR and C. The column never changes, so we don't need to account for that. And then the condition is whether or not the dragon can eat the sheep. So first, we need the dragon to not be in a hideout, because if the dragon's in a hideout, then the sheep can't be eaten. So if grid RC is equal to a £, then we'll return false. So this condition needs to be true, and there also needs to be a sheep in the SRC position. So just to make this make a bit more sense, I apologize for the line being a bit confusing, but this is genuinely how I write my code. It probably makes more sense to write it as something like this, but I just prefer list iterations. So imagine it sort of like that. Basically, for each position that the dragon could be in, we will look for where a sheep that ends up in that spot either before or after the sheep move could be. And those possibilities are r minus turn and the spot above it. And a dragon will eat a sheep in this position if the dragon is not in a hideout and there's actually a sheep in the starting position. Finally, there's also one possibility we need to account for, which is that the dragon is far enough near the top of the board that there's no sheep that could possibly be there. Essentially, that's what happens if SR is less than 0. So we'll say if SR is at least 0 and that prevents the index error here, basically. And so this will represent the starting positions of all sheep that could be eaten by any dragon, by any position that the dragon could be in after a series of this many moves. And so we will union that into the set of possible positions where sheep could have been eaten, and the answer will be determined by simply getting the length of e. And so if we try that on this sample input, we get the expected answer of 27. And then if we check that on our actual input over a range of 20 moves, we get our expected answer. Now, part 3 took me a while to figure out, but we're going to need to change up a lot of our approach. So part 3 changes a lot of things. Firstly, the game begins with a sheep's move. Secondly, there's at most one sheep per column. Third, only one sheep will move in a single turn, not all of them as we previously thought. The fact that sheep is both singular and plural in English gets a bit confusing here, and the problem even calls this out. Fourth, the sheep are not stupid, and so they won't move into a spot where they get eaten immediately. They can still move into a square where they'll be eaten the following turn, but they won't move into the dragon's position unless there's a hiding spot. 6, if at least one sheep is able to move, including escaping off the lowest row, then one of the sheep must move. If none of the sheep can make legal moves, then the sheep's turn is skipped. And finally, the dragon always has to move during its turn. And so the problem is now about finding how many sequences of moves exist wherein the dragon eats all of the sheep. So in this example, we're given a bunch of situations. These sequences can include situations where a sheep deliberately does not move off the bottom row. Basically, the sheep don't have to play optimally, they just can't move into the dragon's position. We're essentially being asked to determine how many legal games exist where the sheep lose. Okay. So this problem is once again going to require memoization, because we're going to find ourselves with a lot of duplicate scenarios. For example, if this sheep moves down, and then the dragon moves here, and then this sheep moves down, and then the dragon moves here, that would be the exact same as if these sheep moved in a different order. Which means that we want to avoid double counting the scenarios after that. So we're going to do this via a recursive search using memoization. So to visualize what I mean, we're doing a depth-first search, which looks something like this. This is our starting state, and then from each state there are a bunch of legal moves that can be made. And so we'll first try one of them, and then recursively call the search function starting here. So that will have its own children states, and so on and so forth. Once we're done summing up all of the possible sequences, we will return to this position, and then continue iterating on here to the next position and try again. This is called depth-first search because we first go down an entire sequence until we determine whether or not it's valid. And then we go back up, and then we go back up like so. And so, unlike breadth-first search, which iterates the states in this direction, we start by going to the deepest extent of an entire sequence, and then only go up a level once we've exhausted our tree. And there will be many duplicate scenarios along this search path, which means that we want to memorize the results, so once we see it again, we can just immediately solve it without needing to do all the recursion again. Okay, so we're going to keep some of our utility functions, but discard the rest. So we're going to define a function using the functools.cache decorator that I introduced in a previous video. What this does is you can put @functools.cache in front of a function declaration, and it will automatically do the caching for you and store the result of any prior computation and automatically return it. One thing to note is that all of the parameters to a memoized function have to be hashable. I'm not going to explain hashing in this video, but it's essentially a way to turn an object into a number such that you can more easily refer to the cache later on. This is why sets and maps do not take linear time to look up and are rather closer to constant time, or rather they are constant time. It's because of this hashing algorithm. You cannot hash lists among other things. And so all of our parameters are going to need to be tuples, because tuples are immutable, and we have to ensure that the object is immutable in order to be able to properly hash it, because otherwise the hash could not account for the values within the list changing. So our count function is going to take a couple of things. First, we're going to take the list of all of the sheep. Or, yeah, we'll take in a list of all of the sheep. Secondly, we will take the dragon's position. And thirdly, we'll take a variable to indicate whose turn it is, which is initially the sheep. And our count function is simply going to return a number, which tells us how many sequences result in the dragon eating all of the sheep starting from this state. So, if the turn is currently the sheep's turn, then we have a couple of possibilities. If there are no sheep left, that means that the dragon has just one, which means that we can simply return 1. There is one sequence from this position, which is simply the empty sequence. This is basically returned at the end of each of these searches, where we get to this point, the last sheep is eaten, the dragon passes turn to the sheep, and then there are no more sheep left, so the dragon wins, so we return the empty sequence as the only option. Otherwise, we'll begin a total count. We'll also count the number of possibilities for the sheep's moves, because it's possible that no moves are able to occur. So, for each sheep, we'll keep track of its index, and I'll show why later. For each sheep, we'll see if it is able to move. So if its current row is the last row, which has the index of the number of rows minus 1, then that means that this sheep is able to escape. So there's one possible move, so we'll increase moved by 1. But in this case, if one of the sheep escape, then that sequence is invalid, so we won't modify the total. The reason we do moved plus equals 1 here is because at least one sheep has to move, which means that if a sheep is able to escape and no other non-escape moves are possible, then the sheep can't deliberately not move to allow the dragon to still win. If this is the only move, then that means that this entire sequence is invalid because the dragon has let the sheep escape and the sheep cannot deliberately lose. If that is not the case, then we check whether or not the sheep is able to move. So, the sheep is able to move if the next spot that it would move to is a hideout, or if the dragon is not currently in the next spot. So if either of those are the outcome, then we'll increase move by 1 and increase the total by the number of possible sequences from this position. So we'll modify sheep, which I'll get back to in a bit. The dragon won't be moving because it's not the dragon's turn, and we'll pass the turn over to the dragon. And then to modify the sheep, we will do this. So the first I sheep do not move, and then the last few sheep after the sheep at index I do not move either. The sheep that moves is the sheep at index I, which is RC, and it moves to position R plus 1C. So essentially what we've done here is we've reconstructed the tuple of sheep and modified the sheep at index I. Because we're reconstructing a tuple, we are not modifying or mutating the value of the original sheep variable here, which is integral because the fact that we are unable to do so is the whole point of using a tuple in the first place to allow the caching to work. So essentially what this is saying is if a sheep is able to make a move down, then we'll add all possible sequences starting from our current state with that sheep then moving down by 1. We'll add that to our current total. If the number of moved positions is 0, that means that there are no moves possible for the sheep, which means that the total is going to be 0, but that total is invalid. So instead we'll return the recursion of simply making no sheep moves at all and passing the turn to the dragon immediately. Otherwise we'll just return the total. If the turn is currently the dragon's, then that means that there is at least one sheep left, because after the last sheep is eaten, it will always have just passed turn from the dragon to the sheep, so this check is all that's necessary. So we'll look at all possible moves for the dragon. So for our C in dragon can move 2, we'll make use of that utility function again. We'll see if the dragon, or rather, we already know that the dragon for sure can move there, because this function already accounts for the out of range issue. So now we just need to increase the total by the recursion. And so we'll get back to modifying the sheep in a moment. The new position of the dragon will be RC, and the turn will pass over to the sheep. The change that will be made here is simply deleting the 1 or 0 sheep that is eaten. So we can do this. Tuple srsc for srsc in sheep. And then in order to remove the sheep that gets eaten, if there is any, we'll do an if check. So a sheep survives and therefore passes the if clause if it is either in a hideout or the dragon is not in that position. Like so. So basically, the sheep that survive to the next iteration are the ones that are hiding or that the dragon did not attempt to eat. And that, again, will then just return the total at the end. And so finally, we just need to actually find all of the sheep. So sheep will begin as an empty list. If the value is equal to s, then sheep.append rc, and then we'll turn sheep into a tuple, like that. And so the final answer will be the count starting with the sheep and the initial dragon position. So let's grab this test case and see if that works. Okay, we get an answer of 1, which is clearly incorrect. And that is because I messed up here, and rather than checking if the length of the sheep was 0, I just checked if it was, i.e. if it was non-zero. So that's the exact opposite of what I wanted. Okay. And then the other issue is I forgot to enumerate the sheep to get the indexes. So that gives us our expected answer of 15. Let's try for this test case, and we'll see that there is an issue that we... No, there is no issue that we didn't account for. Interesting. I thought I was missing something. Okay, it turns out that actually is correct. I was fully expecting to run into an issue here with infinite looping because something that I did in my original solution, because I made an unrelated mistake and was trying to figure out what was wrong, was I thought there would be a possible situation where the dragon could potentially move back and forth between 2 spots indefinitely, and thus that would cause infinite recursion. But I guess that isn't an issue now that I think about it, because if the dragon is blocking a sheep in one position, then when it moves away, it'll unblock that sheep, which means that there will be a valid sheep move, which means that the sheep has to move. So we can't end up with multiple consecutive forced dragon moves, I guess. Okay. yeah, it turns out that that consideration is not necessary. So I guess there we have it. I guess we have our solution for part 3. You'll notice that the actual solution takes a considerable few seconds to run on the input. Given the extremely large size of the output, I don't know if there really is much of a better way to do this. I'm sure I can make some constant factor optimizations by improving some of the logic, but overall, I believe this should be somewhere in the range of optimal. Again, do let me know if you find a solution that ends up working a lot faster than this. I am very much interested in finding optimal solutions to these problems, even if the main competition is to actually write the code the fastest. I am still interested in looking for the optimal algorithm. In any case, that's all for this video. Have a good weekend, and I'll see you on Monday for day 11.